Welcome to the analysis of covariance, or ANCOVA tutorial and RStudio walkthrough. So again, this is just another one in a series of data analysis tutorials and walkthroughs. So again, we ask you to do probably more statistics than you want to, right? But that's because statistics play a crucial role in the scientific process, right? We can use them to summarize our scientific information. That's what we use descriptive statistics for. We can use them to estimate population parameters. And then what we do most commonly in this course, or these courses, or our test hypotheses, right? Inferential statistics. We want to test our specific experimental hypothesis. Remember that statistical hypotheses and experimental hypotheses are not the same thing, right? We design experimental hypotheses to guide our thinking and experimental design when investigating a potential biological relationship between our variables of interest, right? Statistical hypotheses are specific to the analysis that we're doing, right? We have null and alternative hypotheses, H0 and HA abbreviation, right? And the wording for these is specific to the analysis. And for ANCOVA, we actually have probably 3 real sets of null and alternative hypotheses that we can test doing a single analysis of covariance, right? So let's again consult our statistics roadmap. Okay, what we've been working throughout the semester. All right, and here's ANCOVA over here. So we have one continuous y. Remember, y is also denoted as our dependent variable. So our dependent variable needs to be continuous, and then we have both continuous and categorical x variables, or independent variables. More specifically, we use analysis of covariance to compare 2 or more regression lines by testing for the effect of a categorical variable on a dependent variable while controlling for the continuous covariable, or covariate. Okay? So we need 3 variables to do that, right? And we can test for the slopes and or intercepts of these lines, and if they differ among our groups, or if the lines themselves are related to the covariate. Okay? So for example, we could look at head size and body size and see if males and females differ in that relationship, right? So we've got, let's say, head size is our dependent variable, body size is our continuous independent variable, and then male versus female would be our categorical independent variable, right? So again, we're over here in our roadmap, and we really need 3 variables in order to conduct an ANCOVA: a continuous dependent, a continuous independent, and a categorical independent. Okay? So we're expanding on this linear model, right? So y, our dependent variable, is equal to some influence of our categorical variable, which we'll call A, plus the influence of our continuous covariate, we'll call B, and the interaction between those two, right? And so really in ANCOVA, really these are all just linear models, right? But it's sort of this combination of ANOVA and regression. Considering we've done simple linear regression and analysis of variance before, we're sort of combining those methods in this new model to look at 3 variables at once. Okay. So again, we have our variable interest, our dependent variable, we have our continuous covariate, and then we have some grouping variable. And so really we can we're looking at multiple lines potentially, right? And we can ask a series of questions about those lines and what that means both statistically and biologically, right? So really there's 3 sets of null and alternative hypotheses for an ANCOVA. And so since there's 3 variables, a categorical variable, a continuous covariate, and an interaction, each one of those has a sort of a null and alternative hypothesis we can look at, right? The first one is with a continuous covariate, and that So the null hypothesis is that the covariate is not correlated to the dependent variable, or essentially the slope of the regression line is 0. Really we generally have some prior knowledge that tells us there's a relationship between the dependent variable and the continuous covariate. That's why we're using it as a covariate, right? But we still have to evaluate that parameter in our analysis. So that's our first null hypothesis. The alternative would be that the covariate is correlated to the dependent variable, or the slope of the line is not equal to 0, right? The second null hypothesis is that the slopes of the regression lines, we'll call those B, are all equal. In other words, the slopes of the regression lines, or the regression lines themselves, are parallel, right? So if we look back here, all these lines look parallel. That's the null hypothesis in sort of our second grouping. So this is looking at our categorical variable, or actually no, this is our interaction term, I apologize, right? So this is the relationship between our categorical variable and its interaction with the covariate. We're assuming that those slopes of those lines are all parallel, right? Or how the covariate changes, or how the dependent variable changes with the covariate between groups, right? And so here we're testing if the slope of the line is equal to 0. Here we're testing to see if the slope of the lines are the same or not, or parallel, right? And then lastly, we would test the intercepts of those regression lines, which we'll refer to A here. So where they cross the y-axis. This is essentially looking at the effect of the grouping variable. So if the magnitude of that intercept differs between the categorical variable, again, the null hypothesis is that they're all the same. The alternative is that they are not all the same, right? So again, we have three sets of null and alternative hypotheses we can actually interpret from a single running of the ANCOVA, right? So let's talk about what those are. So again, we're looking at comparing regression lines by studying the interaction of the categorical variable, often called the treatment effect, with the continuous independent, or the covariate, okay? And so if we go back to our model, right, so we've got our categorical variable, our covariate, and then our third term is an interaction between those two, A times B, right? And so keep these three parameters in mind. We have a null and alternative hypothesis for each one of these parameters. Okay. So let's take a look at the interaction term first. That's the interaction between the categorical or grouping variable and the covariate. If that term significantly differs from 0, right, the beta parameter there, that means that the effect on the continuous covariate on the response depends on the level of the categorical factor. In other words, the regression lines have different slopes. They have different patterns. How the dependent variable changes as we change the covariate. So if we go back to our first example of head size is our dependent variable on the y, body size is on the x. If we looked at males versus females, if we had a significant interaction term, that would mean how head size changes as the snake grows, or the individual grows, right, differs between males and females. Those slopes are not parallel. If we have a significant treatment or categorical variable effect with no significant interaction, it shows that the covariate changes the same across all levels of the categorical factor, but that the intercepts are different. So the magnitude or the intercept of those lines might be different. So the lines can be parallel or they can be different. If they're different, we really if the slopes of the line are different, we don't really pay attention to the interactions, because it's almost guaranteed that the interactions, or not the interactions, the intercepts, I apologize, are different. If the lines are parallel, we can still look at the intercepts to see if the intercepts are different. So that might mean that one group at a particular body size has a bigger head all the time, right? And so one line is always above the other, right? Meaning that that one group might have a higher magnitude of the dependent variable at any level of the covariate, right? If the treatment effect is not significant, nor is the interaction with the covariate, right? and just the covariate is significant, that means we basically just have one regression line. So if our treatment variable or categorical variable is not significant, the interaction term is not significant, it's more appropriate just to do a simple linear regression than it is anything else. But if the interaction term is significant and or the treatment variable is significant, then the ANCOVA is the most appropriate thing to do. Okay? So again, this gets a little more complicated than the other analyses that we've done, because it essentially is doing multiple things at once, right? So again, we have our response and our covariate, right? And then our grouping variable. So think about multiple lines on a simple linear regression. If the slopes are parallel, that's what the interaction term is looking at. So if the interaction term in our model, and we'll see some examples here, is not significant, that means that the lines are parallel. If the interaction term is significant, that means our lines are not parallel. And they could be going any number of ways, right? It's just whether the slopes are the same or not, or if the lines are parallel or not, right? Even if the interaction is not significant, we can look at the intercept. If this group 1's intercept is different from group 2, again, think about what that means here is that group 1 always has a higher response for any value of the covariate than group 2, right? And that's biologically relevant. If the interaction term is significant and the slopes differ, it's almost guaranteed that they also have a different intercept term, right? But ANCOVAs really are very interesting. They allow us to look at multiple biological relationships or interpretations with a single analysis, right? And so while, yes, it gets more complicated, we can go through all three parameters and interpret what that means biologically, right? So both differences in intercepts and slopes can be biologically meaningful, and then the whether there's a relationship between the covariate and the dependent variable is also biologically meaningful, right? So differences in intercepts are interpreted as differences in magnitude, but not necessarily rate of change. Differences in slopes are interpreted as differences of rates of change, or allometric relationships often, right? And both those things have important biological interpretations, right? So while ANOVAs and simple linear regressions are important and appropriate given the proper data sets, when we have three variables, a continuous dependent, a continuous independent, and a grouping variable or categorical independent, ANCOVAs allow us to look at three levels of interpretation within a single analysis, right? So again, we generally look at the slopes first by testing the interaction, and then we go from the interaction term to the categorical, and then from the categorical to the continuous. Although really the order that you interpret those is not necessarily as important as interpreting them correctly, right? But we'll walk through a couple examples here, and then we'll show you how to do it in RStudio. Okay, so let's look at the first example. There are three species of crickets: X, Niv, and Fake. The species then is our categorical independent variable, right? So there's three species, there's three different categories. Temperature is our continuous independent or our covariate. And then pulse rate of the chirp is our continuous dependent variable. So what questions would an ANCOVA allow us to answer? So let's start with the two continuous. So if pulse rate is our y, temperature is our x, one of the first ones would be is there a relationship between the covariate temperature and the pulse rate of the chirps, right? So that's our first relationship we can look at. When we take into account the third variable, if we look at the interaction between temperature and species, we could test if the slopes of those regression lines are the same, right? So the null hypothesis is that the slopes of those lines would be the same. The alternative is that at least one is different, right? And that would tell us if the chirp rate changes differently across the species as temperature increases or decreases, right? And then if we just looked at the species variable here, our categorical variable, we'd be able to test whether our intercepts are the same or not, or the magnitude of chirps, or essentially how often they chirp at a given temperature is the same between species or not. Okay. Again, I'll show you in RStudio, so don't panic, but again, we really just read our CSV file. We do a linear model, LM. So pulse is our dependent, our Y variable, tilde, and then our continuous and categorical. Notice that I put this little asterisk here, the multiplication sign on your number pad. That will give me 3 variables here. It will use temperature, species, and then the interaction between those two. If I just do plus there, it won't do the interaction. Okay. And then I can ask for the summary of that, which spits out individual beta parameters, and I'm going to caution you not to look at that too much now. Certainly that's important information, but at our level we're going to sort of ignore that, and we're going to move to the ANOVA of table of our ANCOVA, which spits out the results here. Right? We can plot that using our scatter plot, and then if we remember our regression, we use this AB line, right? And we can look at the regression line for each of the 3 species. So X is in red, fake is in blue, nib is in black, right? And we can see how we can visualize the data, right? So if we go back to the results here, so here's our plot, here is our ANCOVA output, and really we want to pay attention to this table right here, the analysis of variance table. That gives us our 3 variables, temperature, species, and the interaction. See how it says temp colon species, that's our interaction term, right? And so we can go through then and now interpret each one of those 3 sets of statistical hypotheses. So let's start with the interaction term, temp by species. The p-value here is 0.4. Here's my f value of 0.9. Degrees of freedom 2 and 42, right? So the interaction term is not statistically significant, right? A p-value of 0.4. The interaction is about whether or not the lines are parallel. Since it's not significant, we cannot reject the null hypothesis, and that suggests that the slope of these lines are all parallel. And that's what our plot would also suggest, right? These lines look parallel. Right? Now we can go to, let's go species. So that's our categorical variable. The p-value is 2 times 10 to the negative 16th with an f value of 1,367, degrees of freedom 2 and 42. That one is obviously significant, right? And remember, the categorical variable, in this case species, is testing for intercepts, right? So the intercepts here are significantly different, or at least one intercept is different than the other 2. We would have to do a pairwise comparison to figure that out, right? From the plot, though, it looks like fake here have a much higher chirp rate at any given temperature than the other 2 species. So the lines are parallel, so we know that they'll never cross, right? And fake is up here. The other 2 are much closer together. So this species has a much higher chirp rate or pulse rate at any temperature, right? So there the intercepts are significantly different. And then temperature or covariate, we probably should have checked this first, to be honest with you, to make sure the covariate was appropriate. In most cases, though, we've already done a simple linear regression to know we're selecting the correct covariate. And this one is also significant, right? And so there is a relationship between pulse rate and temperature. How that rate changes with temperature is the same for all species, but the fake species has a higher pulse rate at any given temperature than the other 3, right? And so we can reject the null hypothesis on temperature, we can reject the null on species, but we cannot reject the null on the interaction term, right? Which again, rejecting the null on temperature, the alternative is that there is a relationship or correlation between temperature and pulse rate. rejecting the null on species. This is saying that there is a difference, at least one intercept is different, right, between the species. And here we could say that the visualization suggests that fake is different, right? And then the interaction term, we failed to reject the null, right, saying that there is no, or the slopes of those lines are not different, right? So the slopes of the lines are parallel. So again, some interesting biological interpretations with a single run through the analysis of variance. Let's look at one more example before we jump into RStudio. Here I have a treatment, fed, starved, or reverse snakes. This is my categorical independent. CS is head size. That's a continuous dependent, so that's what we're interested in, is their head size. SVL is their body length, right? That's our continuous independent or a covariate, right? So with an ANCOVA, what questions can we ask? Well, for the covariate, we can ask if there's a relationship between body size and head size, right? Is there a correlation there? With the interaction of treatment and SVL, we can ask if the rate of change of head size as body size changes is different between the treatments. And with treatment, we can ask if the intercepts or the magnitude is different among treatments. Okay, so at a given body size, is there a head size difference among treatments, right? Again, we read our CSV, we do our linear model with LM, again, CS tilde, so this is our Y tilde, SVL is our covariate, times our categorical variable. We can do the summary of that and then output the ANOVA table, right? So the ANOVA table is where we want to do our look for our interpretations. We can also visualize that, right? Again, in this case, the lines do not look similar as in our last example. So let's look at both our visualizations and our results at the same time here. So here's our ANOVA table. We can look at the p-values. All of our p-values are less than 0.05. Again, we'll start with the covariate. There is a relation, so this is 2.332 times 10 to the negative 9th. Large F value, degrees of freedom 1 and 40. Again, reject the null hypothesis, accept the alternative hypothesis that there is a relationship or correlation between SVL and CS, or head size, essentially. Remember, CS is my measure of head size. Okay. We go from the covariate, let's go to the interaction, SVL colon treatment, right? Realize it does not matter what order I put these in. Okay, so last time I had the categorical colon covariate, this time I have them flipped. It doesn't really matter. Okay. My interaction term, 0.02, F value of 3.96, degrees of freedom 2 and 40. Again, that is significant. We reject the null and accept the alternative hypothesis that the slopes of the lines are not equal. Notice that all we're saying is they're not equal. We're not making any specifics about those. It does appear that, you know, the fed snakes have a much more positive relationship, while the others might be a little flatter, right? But again, we would have to do another round of analyses to look at those actual values to see who's different from who. Okay? But right now, the interaction term is telling us that the slopes of the lines are not equal. We're rejecting the null, accepting the alternative hypothesis there. And then treatment, again, 2.122 times 10 to the negative 5th, F value of 14.25, degrees of freedom 2 and 40. Again, I told you when the interaction is significant, or we reject the null with the interaction term, it's almost guaranteed that the intercepts are also going to be different, right? Again, here it looks like reverse snakes have start off with a larger head size, but that fed snakes end up with a larger head size, right? But since the slopes of the lines aren't parallel, it's almost guaranteed that the intercepts will be different unless we force them through the origin, which is a whole other story there, right? So we don't interpret that as much when the slopes are already different. We try to focus on the rate of change differences rather than the magnitude differences when the slopes are different. Okay, but again, we can interpret each of the three variables in turn and what they each mean biologically, rejecting or accepting the null hypothesis for each of those three parameters, right? our covariate, our categorical, and our interaction term. 3 parameters in ANCOVA, therefore we make 3 interpretations, both statistically and biologically, for every ANCOVA that we run. What are our assumptions? Samples are random and independent, homogeneity of variance, and normally distributed. Essentially all the same assumptions of a linear regression and an ANOVA. Okay. So let's look at this in RStudio. Let me zoom in a little more for you here. So again, first thing we're going to do is set our working directory. That's the first thing we always do, right? And then we're going to read our CSV file. This one's going to be a roach metabolic rate and body size for 3 different species of roaches. We've done this example in some previous tutorials. We've just never used it with an ANOVA, right? So I'm going to just call my data RMD. Remember that what is before this less than dash is just the object name that we're telling RStudio to assign to this new object we're creating or importing, right? That name doesn't really matter. Yes, RStudio doesn't like some characters, and really you just want it to be short and sweet so it's easy as you have to type it in multiple times, right? But you also have to understand what it is so that if your code is long and complicated, you can always refer back to the correct object, right? For me, this is roach metabolic data, so RMD is what I'm going to call it, right? And then read.csv, this is when I want to import a CSV file. And then in quotations, I put the file name, including .csv. Remember, we always give you the data as a CSV file, so we're always using read.csv and then the name of that file. I run that, and now I can see over here, RMD pops up 114 observations of 5 variables. If I want to see what my data looks like, I can use the view command. So I have species, dubia, red runners, or hissers, mass, and VCO2. As you probably know by now, we have to log transform those. So here's my log mass and log VCO2. Okay, so there I can see my data. Now I'm going to plot the data, and I'm going to do it as a scatter plot, right? Before I draw my regression lines. So I'm going to use the plot function. Remember, in plot I can do x comma y or y tilde x. Okay, so you're going to see 2 different versions of this plot function. They're going to basically make the same visualization, right? So here's my x, RMD is my data, my object, $ tells RStudio what variable in that to look at, log dash mass. That's my x, comma y, RMD $ log VCO2. Okay, comma xlab, I'm just telling it what to label the x-axis, ylab, what to label the y-axis, and then main, what to put as the main plot title, right? If I run this, boom. Okay. Again, I could change my color and my shape with PCH and all of those other things. I'm not going to do that in this case. I'm just going to do open circles, black. Okay. But here is my scatter plot. Now if I do the same thing, but in this case I'm doing it slightly different. So now it's my y variable, log VCO2 tilde, right? So this little tilde right here, then my x variable. So I'm giving the plot the equation of the line, and then telling it what data to look at. Now it's data equals RMD, okay? And then my x lab, my y lab, and my main. Now here I've just changed it, so now we should see over here, instead of body mass, it should be mass 1, just to show you that this new code is working. Everything else should look the same, right? Watch this. Boom. Okay, there's that one. Let's go back and run this one. Watch the title. The title is the only thing that is changing because that's the only thing really different between the code. It's just whether when I use the plot function, I can do x comma y or y tilde x. Okay, it's important that you do those in the right order, or everything else sort of falls apart afterwards. Okay, now I'm going to, well, let me do this a little differently so I can. So now I've got my scatter plot. Now I'm going to finish my visualization first. I'm going to draw my regression lines for each species. So I'm going to draw one regression line just using the data points that are for a particular species. So again, I use this abline function, right? Parentheses LM, linear model, okay? Now I have to do this big long thing for my y. So my data set is RMD, $, the y variable, log VCO2, okay? Now brackets, RMD, $species, here's my categorical variables, equal, two equal signs, and then in parentheses dB, because that's how I have my file set up, okay? So what this is telling the abline is that the linear model is y is equal to log VCO2, but just look at the lines, the samples that are species dB, okay? Here's my tilde, and then I do the same thing for the x variable. RMD, $, now log mass, bracket, RMD, $, species, equal, dB in quotes, and then close the bracket, and then close my parentheses. So this is my equation right here, y tilde x. I'm just changing it, so now behind the y, I have to say in brackets, okay, but just look at this species. Here's my x, and then in brackets, just look at this species, right? And the species need to match so that we're making sure we're looking at the same y's and the same x's rather than the y's of one species and the x of another, right? And then I'm just going to tell it to put that line in forest green, okay? So watch when I run this. Now I get this one line here, and that's for the dubia, the dB, okay? Now I can copy and paste that, and now all I'm changing is the species. So here in quotes it's HS for my hissing cockroaches, and I change the color to navy, okay? Everything else stays the same. I just have to make sure I go to a different species now. So here's the linear regression for dubia, this first line. This is a linear regression for hissing, the second line. I run that, boom, my blue line pops up. Copy, paste again. Now I'm changing the species again. RR are my red runners. I change it in both spots, both times, right? DB, DB, one color. HS, HS, a second color. RR, RR, a third color. Okay, I run this. It runs. Notice that the blue and the red line are really similar, but the forest green line is a little bit different, right? Now I have my 3 regression lines drawn, and now I'm going to put my legend. I can see I've got some spots here open up, so legend bottom right, that's the best place to put it. And then bottom right's in quotations, right? Comma, legend equals C for concatenate. And then I'm actually going to spell out the species so that it's easier for me to copy this and go right into whatever I want to use it for, right? So dubia, hissing, and red runners. Remember, I need to put these in alphabetical order because RStudio does that. Close parentheses, there's a comma there, text.col, so text color. So not only am I going to label the species, I want the color of the species name to correlate to that regression line that I drew, and again in alphabetical order according to species. So forest green, navy red, forest green, navy red. Run this. Well, because I'm zoomed in, it doesn't look as great, but there's my legend. Okay. Now my visualization is done. I've done my scatter plot. I've put my regression lines for each of my categorical levels on there, and a legend. Boom. I could save this, export, save as image, right? For whatever I need it for. Now I'm going to run my actual ANCOVA. So I'm going to just call that roach.ancova. Again, that's just the object name, less than dash, LM, linear model, log VCO2 tilde, here's my y tilde, now log mass times species. Remember, I have to put that log mass dot or times species. If I put plus here, it doesn't do the interaction. I want that times in between my two independent variables. And then I'm going to tell it what data set to look at. Okay, RMD. I'm going to run that. Boom, now I got a new object up here called Roach ANCOVA. I'm going to do the summary of that. I'm going to move this up a little bit. Here's my summary. Now, again, this is important information. I'm not trying to say it's not important, but for our level, we're not going to pay attention to that too much. There is this piece of information that's very important. This is the F value for the entire model. Okay, so this includes all of the three parameters that we're really looking at individually. We want to know if the model itself is significant. My F value is 27.74, degrees of freedom 5 and 108, and a p-value of 2 times 2 times 10 to the negative 16th. Okay, so the overall ANCOVA model, or the overall model of the ANCOVA, is significant. Okay, that's good, right? So, well, not necessarily good or bad. It is what it is, right? But we need to understand if my entire model is significant or not. But now I want to dig deeper and interpret the three parameters that I'm really interested in. So I'm going to look at the ANOVA table. So ANOVA, Roach ANOVA, here it is, right? 1, 2, 3. Log mass, species, and the interaction term. Okay. Let's start with the covariate log mass. Again, given everything we've done with metabolic rate and body size, we knew this should be significant. P-value or F value of 132, degrees of freedom 1 and 108, p-value of 2 times 10 to the negative 16th. Okay, there is a correlation between body mass and metabolic rate. We knew that. We're just confirming that. Great. Let's go to the interaction of log mass and species. F value 0.0332, degrees of freedom 2 and 108. P-value of 0.967. We cannot reject the null hypothesis here, and we can conclude that the slopes of the lines are parallel, are all the same, right? And so while, I mean, for red and blue here, for hissing and red runners, you're like, oh yeah, the lines are almost the exact same. But even with dubia here, statistically it's not different from the other two. So the slopes of the lines are parallel, or they're all the same. They're not statistically significant, right? And now if we look at species here, our categorical variable, F value of 2.8525, degrees of freedom 2 and 108, p-value of 0.06. You'd look at this and say, well, because this is how I've taught you, right? You would say that it's below the alpha, or above the alpha, so we would accept the null hypothesis and say that the intercepts of these three lines do not differ. Okay? Hopefully we would move a little bit past that and say, well, it's almost 0.05, right? Because remember, that's arbitrary. Instead of 5% chance of making a type 1 error, it's a 6% chance, right? So it does appear that the intercepts are approaching significant difference here. But again, I would really just ask that you sort of stick to our game plan of accept or reject statement. So this would tell us that we really didn't need to do an ANCOVA. The slopes of the lines are not significantly different. The intercepts, while approaching significant statistical significance, they're not. And so really it's just the relationship between the covariate and our dependent variable. Okay. That's an ANCOVA. I know it's more complicated, but trust me, it's far more interesting. We can make lots of great biological interpretations when we do it, and it's really useful.